right, so today we're going to start section 2.1, which is about numeration systems. And the first numeration system we're actually going to talk about is our own. So the numeration system that you all know and love, digits and numbers and the math that you think of when you think of math, is called the Hindu-Arabic numeration system. Okay? And this is the numeration system that we use today. It was developed by the Hindus and transported to Europe by the Arabs. Properties. There's two properties that you have to have for any numeration system. You have to have numerals. You have to have something, or your symbols, whatever you're using to represent things. And you have to have operations. And you actually have to have a third one I lied. Third thing you have to have is a way of comparing them. So a way of comparing size. So we're going to talk first about the Hindu-Arabic numeration system. And our properties, our first issue is that their numerals are all constructed from 10 digits. So what are the digits in our numeration system? And we stop at 9, right? So the numerals are the single digit values. So we do not have a numeral for the number 10. We have a number 10, but it's not a single digit. It's two single digits combined, not one. So we have 10 digits if you count the number zeros, which is where we start. We also have a place value system that is based on powers of 10. So when we talk about it from that perspective, and we're talking whole numbers here because we're not going to get to decimals until we get to math 2. You start on the far right hand side, we call that the ones place, correct? And the next place over is called what? This is the tens place, and the next place over is called the hundreds place, and we'll go one further. One more would be called the thousands place, and we could keep going with this to the right as far as to the left as far as we need to go. So these are our different powers of 10, and it's a base 10. It's the powers business, it says here, because each one of these can be written as 10 raised to a power. So this one would be 10 raised to the 1. Okay, what would 100 be? 10 to the 2 or 10 squared. What about 1,000? 10 cubed. And so if we keep moving left, they keep increasing in power to the 4th, to the 5th, and so forth. What about the number 1? That is, it's 10 to the 0. And in fact, the number 1 can be written as anything to the 0 power. So if we did not have a base 10 system and we had a base 5 system, say, it'd be 5 to the 0. Okay? Now, any idea why we have a base 10 system? But why did they have a base 10 system? Yeah, and it's not the toes, it's the fingers. It's because you have 10 fingers. So if we were like Fred Flintstone on television and we only had 4 fingers each, because that's what a lot of cartoon characters, especially older characters, have is this, we would probably have a base 8 system, and we would number things and we would count and we would think differently. And we're not only going to be looking at our numeration system, which is base 10. There are others who have different numeration systems that don't use 10. And there are reasons why they choose to use what they use as well. And so we'll get some more of those later. Before I switch to the next slide, though, and talk about another system, I want you to remember this is our numbering system with exponents, which we've talked about before and you've seen plenty of times. The idea that if you have an exponent, this means you have the same value written down, multiplied by itself n times. And we need those powers and that sort of a system and that thinking in order to be able to make sense of some of the numeration systems, not all of them, but some of them, because they don't use always base 10. They use other bases sometimes. Okay? So we're going to talk about the Egyptians next. So this is one where if you've taken contemporary math, you've seen it. I think everybody probably, because I know I teach it, I'm pretty sure Hargo teaches it, and she and I are the ones who taught it in the last few years. You've seen the Egyptian system. Okay? So the Egyptians have several symbols, and none of them look like our numbers. Well, one of them looks like our numbers. The first one does. They have an Egyptian numeral that looks like the number 1. Hang on just a second, too. Have you guys seen me do this before? Egyptian, their first Egyptian numeral looks like ours. It's called a vertical staff, and it has the value 1, so that's convenient. Okay. So when we see that symbol, we know the value is 1, just like ours. The next symbol that they have is a heel bone, and a heel bone looks like this symbol. Again, another symbol that you may have seen used before. We use it in set theory. We use it for unions and intersections. We have seen it there. But it looks like an upside down U. And a heel bone has a value of 10. Their next one is a scroll. A scroll looks like that. And it has a value of 100. My favorite's got to be the lotus flower because I don't draw well. And it looks something like that. That's terrible. Your book has a much better picture, I'm quite sure. Maybe I can try better. That's slightly better. Any guesses what the lotus flower value might be? It is 1,000, yeah. Pointing finger, which doesn't look a lot like pointing finger, but we can pretend it looks like this. I guess it sort of is. What's your pointing finger? How much is it worth? 10,000. Next one is the polylog or Virgo fish, type of fish, and I do not draw these well either. Some of the researchers I've had call this a tadpole. Oh yeah, you see a fish? Pretend you do. And it's worth 100,000. But for sure the most exciting one is the astonished man. And this symbol looks a little bit different in your book than it does in my contemporary math book. So we're going to draw it the way that this book does, which looks something like this. And I think he's astonished because he's worth $1 million. So I don't expect you to memorize the symbols. I don't expect you to. They're difficult anymore. But you have a note card of your tests. Well, and it's test 2, so this is something that you can refer back to as you're doing your notes. Okay. But we do need to know how to work with these symbols and to be able to go both from, most conveniently, from their numerals and into ours and back and forth. But this book primarily focuses on thinking about how their numerals or how their system would be thought of if you were in their system. In other words, put on your Egyptian hat and walk like an Egyptian with me for just a little bit. Okay? You're going to pretend you're an Egyptian, which means you don't know anything about number 1, 2, 3, 4, 5. You don't know anything about America either. Right? Because it just wasn't here. So you have a value and you're an Egyptian and somebody owes you money to the tune of 3 scrolls and a heel bone. Now, you might in your mind think of what number that is, and if you do, that's great. But if you're an Egyptian, you wouldn't turn this into our numerals, because our numerals don't exist yet, right? Okay. So the Egyptian numerals, what we're wanting to do is we're wanting to focus majority-wise anyways on what number comes before and after a numeral. Okay? So what number would come, let's do after, because this one's easier to do after on, so let's go to B first. What number comes after 3 scrolls and heel bone? That's right. 3 scrolls, a heel bone, and a vertical staff. Right? Because it's one more. This is one more than it was before. Because that's what number 1 is. It's a single staff. And if I had some numeral and I was trying to go backwards and I wanted to take one off of a single staff, I just remove a single staff. But part A, which is asking me to go backwards, doesn't have a staff to remove, does it? So what am I going to do? So what do you want me to do, Brendan?
3 scrolls, vertical staff.
like this. So you want me to act like a Roman. Actually, it's not. That's a good idea. We're going to talk about Romans, I think. The 3 scrolls is right, so let me erase this part. So how much is the heel bone worth? Not in our numbers, but how much is it worth in their symbols? If I took a heel bone, I could turn it into 10 staffs, right? Those are equivalent. Are you with me? So if I took a heel bone and I turned it into 10 staffs, kind of like taking a $10 bill and turning it into 10 ones. So that's in essence what we're doing. What would I do then to have one less? I'd have 9 staffs. And they do have, in some books, you'll see them stack things on top of each other. I don't think this book does so much, but if you've used the other textbook for contemporary math, you probably would see this written like this. So you have the right number like that. So either way is fine. It doesn't matter. Stacking or stacking. But this is the number that comes before. It's kind of like subtracting, right? If you had $50 and you wanted to subtract 1, you can't do 0 minus 1. You have to turn the 0 into the number 10 by borrowing. And that's in essence what you guys just did for this particular one. Now, note, I'm going to show you notes on the bottom of each of these of why their systems maybe aren't still used today. How's that? There's a reason why we use what we use, and there are some inherent flaws in their systems. And the problem, if you will, on this one is that that very first one becomes cumbersome to write. And if you had to write down 9 astonished men, and 9 scrolls, and 9 heel bones, and 9 staffs, it's taking a lot of space up. Even if you don't think it's taking a lot of time, it's taking a lot of space. So this isn't especially efficient. All right, so let's do another system. The Babylonians. The Babylonians are kind of cool because they only have 2 symbols. So that's kind of friendly. So their system has a symbol that looks like an upside down triangle, all filled in. And they have one that looks like, kind of like a less than sign. It's a little more boldened. It looks something like this. It's terribly sloppy, but you have the right ideas. The triangle, the first one, has a value of 1. And this symbol has a value of 10. That's it. You might look at that and say, but how am I going to write the number 152? Surely you don't want to write 15 of those 10s out, right? The answer is no. What they did is somewhat of what we do. Right? They actually have a positional system. So in our system, for instance, when we write the number 352, that 3 doesn't mean 3, it means 300. So the location of where it is actually depends, that location makes a big difference, right? Same thing with their system. They have a positional system. So their place value system is actually a base 60 system, and so they have locations much like we do. So here's the ones place, just like we would have. And then since there's base 60, they'd have the 60s place, not the 10s. They don't have base 10. What would the next one be? 60 squared, just like ours goes from 1 to 10 to 10 squared. There should be 1 to 60 to 60 squared. And we can keep going up from there, and 60 cubed and so forth. Okay, so they have these systems and it's all base 60 stuff. So, the question is, what do they do with theirs then? So let me show you an example. And we're going to do the same thing we did on the last slide, where we're going to look at what comes before and what comes after. Can I switch the slides? Good. Okay. So the symbol that we're going to use, give yourself some space or just write it over to the side, because that's what I had to do. I want you to do a triangle. And then 5 of these guys. Okay, I'm just going to draw them as less than signs and not bold. Okay with that? Awesome. All right, and then we're going to draw 9 of these. need to talk a little bit about what they do in their system. So we can interpret what the heck this is. Because it looks like a lot of symbols repeated. It's what it is, it's lots of symbols repeated. All right, so in their system, if they have the unit that's a 1, which is the triangle unit, it would come on the right-hand side of the tens unit. Okay? So this right here could legitimately all be in the ones place. Okay? So the triangles worth single digit 1. I have the less than looking signs worth 10. So count them up, just so that you guys can have a sense of what this number is. What do you see all in red underneath there right now? 59. Because there's 5 of the less than's, right? This is 59, which is the largest number they would write, actually, 59. Because if they had 60, they'd move over to the next place value system, because it's base 60, right? It's kind of like when we get to 10, we don't have a single digit anymore, we have double digits. Okay? So same thing here. They wouldn't be in that place value anymore. But this place value right here would be the 60s place. Okay? We have ones place, you have the 60s place. And we can have more stuff over here too, if they're more larger, and that's fine. All right, for this one, part A is the easier one to do. Because what we did, remember back in the Egyptian example, is that in order to take the number before, it's like subtraction. What would you do with this number to get the number before? Just take away a triangle, right? So, because I know how much you love to draw and want to draw this out again, we're going to. You've got a triangle, and then you've got 5 of the less than signs, and then how many triangles are you going to have after this? 8. So when we take our number 10, right, if you had number 9, let's say we had the number 9 in our system, it becomes the next digit up, right? And what that happens is it means I'm adding 2 values, okay? And this 9 turns into a what? A 0. So let me try a number. Let's say we had 39. That's a 4. Let's try 9. What happens when I change this number to 1 higher? What happens literally to the 9? What will it change to in that place? A 0. I won't have anything here anymore, right? And I take the number 3 and I turn it into a 4. It becomes 1 larger in that place, right? So the same thing is going to happen here. This 59, because we counted it, we know it's 59, is going to be turned into a 0. And here's the first flaw that we've encountered in their system is they don't have a 0, which means it's just not going to be there. We're not going to list anything. Okay, so ignore that back for a moment. We'll come back to that. And then the 4, like I wrote down here, the 30 becomes a 4. Right now, in their next place value over, that base 60, where I've got the 60 underneath there, they have a 1. So what will you need now? A 2. And how would I draw 2? 2 triangles. So the number that would come after the one that I just wrote down at the very beginning would be this number. Now, I don't know about you, but that seems like it might cause you little kidney problems. Because that numeral in part B could represent what number? 2. That's a problem, right? Before you owed me like $100 and something. Now you owe me 2? Okay, so this is obviously not good. So it can be interpreted as 2 times 60, which is 120, which is what we mean for it to be interpreted as. 2 in the 60s location, right? It could be interpreted as 120. Or it could be interpreted as the number 2. Or it even could be interpreted as the number, as though they're 2 separate numbers, one of them in the 60s place and one of them in the 1s place. It could be 61. Or many other options as well. Obviously, this has some problems. And hence we don't use it today, right? There's a reason they don't have this system going on. All right. Who's next? The Mayans. Well, so the world didn't end last year. It's good. We're all here, and we get to do some more math. And even though mine said it was going to end. The Mayans have 3 numerals. And they at least address one of the problems the Babylonians had. One of the problems, the first one I mentioned about the Babylonians, was they didn't have a 0, right? The Mayans do. So we've got that considered, that issue considered and fixed. So let me tell you there first. They have one that's a dot. This is the value of 1. They have a horizontal bar. This has a value of 5. And they have a symbol that looks like this. And it has a value of 0. It's like a shell. Kind of what they describe it as. Looks like a football a little bit. Not mine, because I don't draw well, but yeah. And they look a little bit different in different books that I've used as well. But it has this sort of a shape. It's certainly not going to get confused with the dot or the line. That's how you draw, right? So a few things. First of all, they have a place value system, like us, like the Babylonians. They have one's place, they have another place, they have a place value system. That place value system is a modified base 20 system. So let me show you what that means and what I mean by modified. First, they have the ones place, and then they have the 20s place. So far, so good. Let me pause actually and ask you, any idea where they might have base 20? Fingers and toes, and that would make sense if you did not wear shoes, wouldn't it? Yeah, for sure. So that's actually why they're using fingers and toes. Here's the deal now next, though. They do not do 20 squared. They do 20 times 18. It's not just for fun, but let me do the next one. I'll come back to 20 times 18 so you can see why. Then after that, they actually do powers on the, I think I've written this wrong. I think it's powers on the 20. 20 squared times 18. I know that's right, yeah. 20 cubed times 18. And so forth. So their powers for 20 start, but they only start after we do 20 times 18 in that third spot. Does anybody know what 20 times 18 is? Can you find out for us?
360.
It is 360, very good. 360. What's the value about the number 360? Degrees in a circle. Another one. Almost the number of days in a year, and that's actually the one that we would use. The circle thing happens to be from the Mayan system too, so all those are related ideas. And so they were using a base system that they thought had a modeling of the year calendar, how we would anticipate the Earth rotating and whatnot. All right, so even though I've sort of written this like this, I've already written it wrong because number 3 you see here is that they write things vertically. The highest place value is at the top and the lowest place value is at the bottom. So their system actually looks far more like this. Here's the ones place. I'm just going to leave a space next to it. This bar is not vertical bars up here. Okay, I'm just leaving that as a space. This would be the 20s place. This would be the 20 times 18s place. 20 squared times 18, 20 cubed times 18, and so forth. Okay, so it's written vertically from bottom smallest to top the largest, highest. And this last piece right here about the bars, their bars go beneath the dots. So if you have the number, say, 7 would be a bar because it's 5, and then you put the dots on top of it. Okay, so the dots are on top of the bar. That's what I'm talking about. So the dots being on top of the bar gives you some indication anyway of how to differentiate the place values. So let me do one of those so you can see how it looks. So we're going to do 2 dots. and a bar, and then 4 dots, and a bar. Let's go with that. Okay. Unfortunately, this still isn't 100% clear because we could still draw things in a variety of ways of where the place value systems are. But let me draw the one that would be most natural for what we're using here, okay? Most natural would be to say that this is where the values break apart. Okay, so this right here would be the ones place, and this would be the 20s place. Again, this isn't ideal, and we'll see why here in a minute if we think of it, but this is a natural way to break apart. Okay, so the break has to occur for sure right at that dotted red line. You have no options there. Because you would not in one of the place values have the dot beneath the line. Okay, dots are always on top of the line. Okay, everybody good with that? Right. So we understand that this is 7 and this is 9. Does everybody understand that okay? 7, 9, we're good? Okay. So let's do the number before. That's the easier one. If you wanted the number before this number, what would it look like? 3 off the bottom. Make sense? Because what we really want is we want this 9 to be an 8. The 9 just needs to be one smaller than it currently is. And the way that you change the 9 into 8 is you remove one of those dots. So the number before this number would be 2 dots and a line, 3 dots and a line. Just remove it off. The number after this looks a little different. So in essence, I want the 9, because it's the bottom place value, just like the 9 at the end of our number in our number system, to turn into a 0 or 10. We want it to get larger, right? And in their number system, it can turn into a 10 because they have base 20 number systems. So how do I turn 4 dots and a line, which is the number 9, into the number 10? Make the 4 dots into a line. I have 2 lines. But on top of that, I have a line and 2 dots. You see the problem with this?
Why would you use the football?
Because the football is a 0, and if you put it in there, it doesn't separate the numbers, it creates a place value. So let me show you what would happen. If you put in, because see, we use a 0 for 2 purposes in our number system, and it's happening at the same time. But if you did this, which is what I think you're telling me to do, like that, put in a 0.
Well, I was thinking like a variable.
Okay.
If we were to turn everything on this side,
Let me do
what
it.
we do? Yeah.
Okay. Then this means you have 0, 1s, and now what? Are you supposed to have 0, 1s? You're supposed to have 10 ones, right? Because the ones place value is supposed to have a 10 in it.
So that makes the bottom one that you just drew out makes it look like that is completely empty.
That placeholder is completely empty.
So instead of 10 being there, there's a 0.
Yes.
0, 0 there.
Yeah, see, because we use the number 0 in our place value system to do multiple things. We use it to separate places, right? Like the hundreds place and the tens place or something like that. We use it to separate the place values. We also use it to represent that there's a 0, as in there aren't any of this kind of a number. And they're not using it as a separator at all. Okay. Yes?
So can you explain why that third bar you had just 5, how that makes sense?
Over here?
Yeah.
Okay, so what we did is this still stayed the same 7 as before. This right here is the number 10 because each bar is worth 5. Okay, so what we have written down is correct, but obviously it has problems. Because if you just started with that value right here, this has another number it could equal.
If they go up with this, so it would be
Right? What would you say?
like your 79.
That number's not 79. That number is 720s. Think like in terms of dollar bills. Like if you only had $1 bills or $20 bills, you have 7 $20 bills, and you have, in this case, 9 $1 bills. Okay? So it's like taking now those $1 bills, and we've got 10 of them now. we've got 10 $1 bills. And then we still have the same $7 $20 bills. Okay, so here's the problem with this though, is that I drew those little red lines in there, but the way that this is written, you didn't get there the way we created it because we went from this number into another number. This number could very easily be read as 17. 5, 10, 15, 16, 17. This is what you would do if you were writing down the number 17. But we didn't mean it as 17, right? It's all good. Bookkeeping problems. Please don't be an accountant if you're a Mayan. This would be a problem. Bankers can have all kinds of problems. This could be read as 17. We're reading it this way. This is how we meant it, right? We meant 7/20s. There's a 7 in the 20s location. And then we meant 10 additional in the ones location, 150. That's what we meant it to be. This is what we were intending. But unfortunately, that is exactly the same way as you'd write the number 17. But in reality, we could separate it in lots of different ways. We could have said, okay, well, we could also separate there. If you have 5 in the ones position and you have 5, 10, 12 in the next position. Or maybe you have another one of these right here. You've got 5 in the ones and you've got 5 in the 10s or 20s, and you've got 7 in the 25s, 18s, and 360s. There's no way to differentiate that with their numbering systems. Problem? That's probably why they weren't able to predict the end of the world. So
That's what I just said, that's where their calendar was from.
yeah, their calendar had some problems, didn't it?
I got the dots
How would
on
they
one.
have used that? Like, do you think they came up with a way to kind of separate it?
I don't know. I haven't researched it. You know, obviously, there's one of the things they could do is they could just allow extra space between things, right? If you separated them by a little bit of extra space, that would help. And that's a potential. Yeah. Here's-
So on our exam, are you gonna have us say what the value like is?
No. The kinds of options, or the kinds of questions you're going to be doing are what we're doing on A and B. What's the number 4? What's the number after? What's number 4? What's the number after?
How will we spend them?
Like on a test. So if you were explaining what you were doing on a test, you'll be explaining why that actually turns into what you were asked to do. So you'll be saying, okay, this is, you know, I'm seeing 9 in the ones place, so I need to make it 8. Because there's a big way on my dot that should make it 8. And I'm seeing 9 in the ones place and I want to make it 10. The way I get it number 10 in the Mayan system is I do 2 lines. So I change the 4 dots in the line into 2 lines. Okay. I'm not going to have you tell me what other options it could be or anything like that. That's not what your book is doing. I'm just presenting it because I think it's interesting, and I think you can see parts of in some of these things, the reason why these systems, well, they failed. I mean, they're right. I mean, they're not around today, and there's reasons why, and we're sort of exploring some of those reasons why as we're talking. Okay. All right. I think we can do one more. What's next? Just keep Brendan. Romans. Do you remember the Romans? They actually have lots of symbols, kind of like us. We have 10 symbols, right? They don't have 10, but they have several of them. And we do see Roman numerals used today. Where do you see Roman numerals used today? There's lots of places. Symbol! Yes, you do. What else?
An outline?
Sheet music, outlines. Mm-hmm. Clock. Yeah. You will see it in books sometimes, the headers for chapters of books. You see Olympics too. Volumes of things, that's a good one, yeah. So I'm going to talk to you about the Romans again. This isn't your assignment, but this is a trivia piece of information. When you leave this building, you guys, I want you to look at the clock tower. Okay? And I want you to see if you can figure out what's wrong with it. That's the word until everybody has a chance to see it. Okay? Remind me when we get to class next time, we'll make sure everybody has seen it in our. Yes.
On both sides or just on one side, or?
Actually, I was told there's an error in the clock of Bailey by the president. The person who said you should look at the clock of Bailey or on Bailey on a Rayleigh. There's a problem. And I forgot about it, you know, for quite some time, and then I saw it later. Okay. All right, so here are the Roman numerals. What's the first one? It looks like an I. And sometimes you won't see the top of them written at the bottom. It won't actually look like, it'll just look like a stick. What value has the Roman numeral I? 1. What's the next value you know? There's a V. And again, sometimes you'll see it written with a top and a bottom on it. Sometimes you'll see it written by itself. What value does it have? 5. What's next? X. And that's the number 10. And that's the most common ones you see. Does anybody have beyond that? L is next. There is an L and an M. And there's a C. All right, so L's first. What is it, Brendan? It's 50. Still doesn't look very good. All right, C's next. That's 100. There's a D and then an M. D is 500 and M is 1,000. And occasionally you will see older buildings also written like establishment dates and Roman numerals. So you do see that occasionally too. So it was established in, 1763 or something, and they'll write it that way. All right, so they have some interesting properties to their numbers that we don't have in our system. I mean, in some sense, this is interesting and different, but it's a little bit awkward too. So let's take a look at some of their properties. They have 2 sets of properties. I think we have time. No, we really don't have time to get into it. Okay, so let me just say what they are. There's a subtractive property, which you're probably aware of. For instance, the number 9. We don't write out 9 single ones. There's a shorthand way of doing that, okay? Which is what the Babylonians would do, right? They would write out the number a whole bunch of times. What the Egyptians would write out 9 times. Well, there's a subtractive property that keeps us from having to do that. There's also a multiplicative property that you may not have seen before, and that one's an interesting one. So we'll start with those properties next time, and with what's wrong with raising Chapel's Tower, clock tower, when we get back, okay? Have a great weekend, guys.